Hello everybody, today we're going to be talking about Chapter 4. This is a moment of a force. We're going to talk about the scalar formulation this morning as well. So if you think about a moment, you can also, some people think of it as a torque. If you've ever had a bolt, say on an engine or in your house, some type of pipe that you're trying to loosen and you can't get it, you put like a longer bar on that wrench that you have and you pull down on it with the same amount of force, but now you have more distance, so you have more of a moment. So that's when we're talking about a moment. It's just a rotation or a possible rotation around a point. So I've got an example here. I've got a swimming diving board over a pool. Now, at what point does the person that weighs 100 pounds have more moment? We'll call this point A. Which one has more of a moment? Well, we know that these are both 100 pounds. So if we calculate the moment, and a moment is force times perpendicular distance. Perpendicular distance, meaning you notice here that this is causing a perpendicular distance, and this is the perpendicular distance to point A from force 2, and this is the perpendicular distance from force 1. So if we were to calculate the moment, we'll call it 1, of force 1 times distance 1, this is distance 1, and this is distance 2, we could say distance 2 would actually be the whole distance here. That would be distance 2. We would say that the moment 1 is 100 pounds times 5 feet, which would be 500 foot-pounds. Moment 2 would be force 2 times distance 2, and force 2 is still 100 pounds, but now distance 2 is 15 feet, which is going to be 1500 foot-pounds. So you notice just by walking another 10 feet on this diving board, you've created 3 times the amount of moment. So let's take a look at these. I've got a fixed beam, and when I look at a fixed beam, and I draw the free body diagram of this fixed beam, I will always have a force in the y, a force in the x, and I have my moment. And if this is point A, this would be AX, this would be AY, and this would be moment about A. So that's what we have here. So the fixed, it has all these 3 reaction forces. Anyway, so let's take a look at this beam here. So we have, we'll call this point A on each one of these fixed beams. We're going to have that force 1 times distance 1 is equal to moment about A. On this one here, we're going to have the moment about A is force 2 times distance 2. Now which one would have more moment? Well, it would depend on the force, but if the force was equal, we would know that this would have more of a moment. And then the last one here, and this would be force 1 times distance 1 plus force 2 times distance 2. So if you look at this, when I have this beam here, it is making it rotate in a clockwise fashion. So that is going to be negative. So clockwise is equal to negative, and a counterclockwise is equal to positive. Now that's how I always think about it. So if I summed my moment about point A that would equal to 0. That's my formula. Then I could come up and say, alright, moment about A. So if I drew the free body diagram of, let's say, this one here, I'd have force A in the X, force A in the Y, force A in the X, and then I have my moment about A. And I have my force here that's acting at some distance 1. So if I look at everything I have here, if I sum my moment about point A, I have moment about A, so that's part of it. Now since force AY goes into this point and force AX goes into this point, and there's no perpendicular distance, those would be 0. So I don't need to worry about anything that goes into a point or its line of action. And then I could say minus force 1 times distance 1 is all equal to 0. Since this is going in a clockwise, that's negative, negative, and my moment I am showing in a counterclockwise, which would be positive. This would be positive. So in the next video, we'll do some examples to help show you how to calculate moments about certain points given certain forces on different objects. Okay, thanks.